Welcome to today's paper reading. Today's paper is titled, Agent Workflow Memory, Inducing Reusable Routines for Language Model-Based Agents. This paper introduces Agent Workflow Memory, AWM, a method for language model-based agents to learn and reuse task workflows, published on the AR14 preprint by Zora, Zhiruo, Wang and colleagues from Carnegie Mellon University and Massachusetts Institute of Technology. The abstract highlights the challenges faced by current language model-based agents in handling long-horizon tasks with complex action trajectories. In contrast, humans can solve such tasks by leveraging reusable workflows learned from past experiences. To address this, the authors introduce Agent Workflow Memory, AWM, a method that induces commonly reused routines and selectively provides them to guide the agent's actions. AWM is designed to be flexible, applicable in both offline and online scenarios. The experimental results demonstrate significant improvements on major web navigation benchmarks, including a 24.6% and 51.1% relative success rate increase on Mind2Web and WebArena, respectively. Additionally, AWM reduces the number of steps required to solve tasks in WebArena and shows robust generalization across different tasks, websites, and domains. The current language model-based agents integrate a fixed set of examples, which leads to a lack of robustness and an inability to learn reusable task workflows. Motivated by human learning, the authors propose Agent Workflow Memory, AWM. AWM induces workflows from agent trajectories and integrates them into memory to guide future task-solving processes. This mechanism allows AWM to capture reusable skills essential for solving complex tasks. AWM demonstrates significant performance improvements over baselines and operates effectively in both offline and online scenarios. Additionally, AWM shows superior generalization across different tasks, websites, and domains. Figure 1 illustrates how AWM enables agents to continuously induce and apply workflows to improve performance, compared to stagnant baselines. The results shown are from AWM on the WebArena map split as an example. AWM starts with a basic set of built-in actions and solves new tasks in a streaming manner, continuously inducing workflows from the task at hand. This process creates a snowball effect to induce and apply increasingly complex workflows while expanding the agent memory, often yielding a substantial performance gap over a vanilla agent that does not adapt. This gap over the baseline rises as high as 22.5 points on WebArena after rolling over only tens of examples. In this section, we discuss the web navigation task, which involves an agent with a language model backbone L and text-based memory M. The agent interacts with an environment defined by a transition function T. We then introduce the workflow representation, which includes a textual description of the workflow and a series of steps to complete it. Each step consists of a natural language description of the environment state, reasoning for the action, and the action itself. Finally, we describe the workflow induction process, where an induction module I creates workflows from past experiences. This process involves a language model-based module that extracts common subroutines and enhances workflow generality by abstracting out specific contexts. Figure 2 illustrates the AWM pipeline, where an agent takes actions to solve given queries. It shows how the agent induces workflows from successful experiences and integrates these workflows into its memory for future use. Figure 3 illustrates the offline operation of AWM, where additional canonical experiences are available. The process involves two main steps. First, AWM takes in all training examples from a website, concatenates them into a single prompt, and feeds them to the LM to create a set of workflows at training time, I to train, offline. Second, AWM incorporates all induced workflows into the agent memory at inference time to solve test instructions L, Q, M plus offline, OTist, ATist. This setup ensures that the agent uses the same workflow memory offline to solve each test. Figure 4 illustrates the process of AWM Online, where the agent continuously updates its memory by inducing workflows from stream test instructions. The process starts with the default memory M and iteratively predicts actions for each test instruction, transforming successful experiences into workflows that are added to the agent's memory. The figure highlights the memory updating process and the evaluation of the success rate of the predicted action trajectories for all tests, reporting the average score. In this section, we discuss the experiments conducted on two major web navigation benchmarks, WebArena and Mind2Web. For WebArena, our AWM approach achieved superior results, outperforming the browser gym baseline by 12.0 absolute points in task success rate. This represents a 51.1% relative increase. Notably, AWM also surpassed the STEP method, which uses human-engineered workflows, by a 7.6% relative increase. In terms of efficiency, AWM required 2.0 fewer steps per task compared to the browser gym baseline. Moving to Mind2Web, AWM demonstrated high success rates in both offline and online settings. In the offline setting, AWM achieved the highest success rates in both step and task levels, leading to significant improvements in element accuracy. The online setting showcased AWM's ability to generalize across different websites and domains, with substantial improvements over the MindAct baseline. Table 1 presents the task success rates on the WebArena benchmark using GPT-4, with a detailed breakdown across 5 website splits. The table highlights that AWM achieves superior performance, surpassing the browser gym baseline by 12.0 absolute points and showing a 7.6% relative increase over STEP, which uses human-engineered workflows. Additionally, AWM demonstrates efficiency by requiring 2.0 fewer steps per example compared to browser gym, indicating its effectiveness in maintaining high success rates with efficient task completion. Figure 5 illustrates the rapid learning capabilities of the AWM method using a small dataset, specifically the WebArena map test split. The agent shows a fast learning curve initially, achieving higher success rates by acquiring essential workflows. This phase is followed by a stabilization of success rates, demonstrating AWM's efficient learning process with minimal data. Table 2 presents the task success rates on the cross-template subset of WebArena, detailing the performance of various methods across different website splits. Notably, AWM, OURS, demonstrates the highest overall success rate, indicating its effectiveness in cross-template generalization. The table also provides a breakdown of success rates for each website split, with the number of examples for each split clearly marked. Figure 6 illustrates how AWM constructs more intricate workflows over time by learning from previous instances and earlier workflows. Initially, the agent develops the Find a Place by its name workflow by summarizing past examples. Subsequently, when faced with a task requiring the zip code of a location, AWM leverages the initial steps of the existing workflow to locate the place and then adds further steps to retrieve the zip code. This integration of new steps on top of the basic find location task enables the agent to successfully create a more complex workflow, such as get the zip code of a place. Table 3 presents the offline results of the AWM method on the Mind2Web cross-task dataset, focusing on element accuracy, LMACC, action F1 score, and step success rate, step SR. The table highlights that AWM, using both GPT 3.5 Turbo and GPT-4 models, achieves the highest success rates in both step and task levels, outperforming other methods like Synapse and MindAct. The key improvements are noted in more accurate element selection, contributing to higher step success rates. Table 4 presents the success rates of various methods on the Mind2Web dataset across different generalization scenarios using the GPT-4 model. Key findings include AlmaLine's superior performance in cross-domain scenarios, AlmaFly's slight edge in cross-task scores, and AlmaLine's ability to naturally resolve train test distribution gaps. These results highlight the strengths and weaknesses of each method in different testing environments. In this section, we explore different methods to represent workflows. First, we compare a language model-based method with a rule-based method. The language model-based method shows a slightly higher efficiency with a 0.1% difference in success rate and 0.4 fewer steps. Next, we examine the representation of workflows in textual versus programmatic formats. The textual format achieves slightly better element selection accuracy and step success rate but suffers a 1.2% drop in task success rate. Finally, we investigate the use of natural language descriptions versus HTML for environment abstraction. Using only HTML results in a 0.8% drop in step success rate, and combining both descriptions and HTML leads to worse performance due to increased context length and potential contradictions. Table 5 presents the success rate of AWM on WebArena using GPT-4, comparing rule and LM-based induction methods. The success rate gap between the two methods is minimal at 0.1, but the LM-based method uses 0.4 fewer steps, indicating greater efficiency. The LM-based workflows are found to be finer-grained, potentially preventing unnecessary steps and making the task-solving process more efficient. Table 6 presents the results of different workflow induction methods for AWM on the Mind2Web cross-task dataset. The AWM4 LM method shows a 2.8 margin improvement over AWM4 rule. AWM-LM leverages abstract, reusable subroutines, which are more flexible and readily applicable across test examples compared to the full example trajectories induced by AWM rule. This abstract, reusable nature of workflows contributes to the efficacy of the AWM-LM method. Table 7 presents the results of using AWM with code and text workflows on the Mind2Web cross-task dataset. The table shows that AWM text, which uses text workflows, achieves slightly higher element selection accuracy, 51.2, and step success rate, 45.4, compared to AWM with code workflows. However, AWM text experiences a decrease in task success rate, 3.6. This indicates that while both text and code formats can effectively augment agent memory, there is a trade-off in overall task success. Table 8 presents the results of using GPT 3.5 Turbo with different environment representations in the Mind2Web task. The data indicates that natural language, NL, descriptions of states are more effective than HTML representations, as substituting NL with HTML results in a slight decrease in step success rate by 0.8. Interestingly, combining both NL and filtered HTML leads to even worse performance. This outcome is hypothesized to be due to the increased context length and the presence of irrelevant items in the filtered HTML, which may conflict with NL descriptions and hinder the agent's abilities. The ALMA's framework is designed to integrate workflows as part of an agent's action space. This is achieved by wrapping each workflow into a high-level function, effectively creating a shortcut tool for the agent to perform a series of predetermined actions. Initially, the agent is equipped with default, primitive actions such as click and type. ALMA's then adds induced workflow actions like find place and get place zip code to its action repertoire. When a workflow action is called, it triggers a sequence of predetermined steps, such as the login workflow example where a series of clicks and types are executed in sequence. Performance analysis shows that ALMA slightly improves the step success rate and overall success rate. However, the agent currently uses workflow actions in only 18.5% of tasks, indicating a resistance to utilizing newly added actions. Additionally, workflow actions do not always lead to task success, particularly in dynamic environments where real-time state access or dynamic execution loops are needed. This highlights the need for more advanced techniques to fully leverage the ALMA's framework. Table 9 presents the results of the Mind2Web system with the ALMA's variant, which expands the action space in addition to memory augmentation. The data indicates that while ALMA slightly enhances the step success rate by 1.3 points, the overall success rate remains at 3.2, similar to the base memory-augmented AWM. Analysis reveals that agents only utilize workflow actions in 18.5% of tasks, suggesting a reluctance to adopt the newly added actions. Despite this, the expansion of actions with workflows appears to reinforce their presence in memory and provides minor additional benefits as auxiliary actions. Figure 7 illustrates an example where dynamic environment changes pose challenges to the utilization of workflow actions. Specifically, when booking flights, users often input a city name such as New York, but the system frequently presents nearby airports to support the next step in the search. Although a book flight workflow can be induced to enter all required data via a predetermined action sequence, the action to choose pop-up airports is executed without considering the intermediate states with available pop-up options, making it inflexible. This highlights the need for more advanced techniques like real-time state access or dynamic execution loops to address such issues. In the realm of web agent benchmarks, several key works have been instrumental. Zhiruo et al., 2017, introduced MiniWab, which evaluates agents across various scenarios. Liu et al., 2018, expanded this with MiniWab++, adding extra challenges. More recently, Yao et al., 2022, developed WebShop, featuring a simulated e-commerce site with crowdsourced instructions. Enhancing agents for complex tasks involves modifying their action space, such as constraining the search space. Liu et al., 2018, enabling language model self-feedback. Sun et al., 2023, or incorporating human-designed actions. Sadi et al., 2023. Additionally, augmenting agent memory with example demonstrations has been explored. Halupsak et al., 2023. Learning common procedures from experiences often involves using full examples as context. Jing et al., 2024. Extracting reusable subroutines with rule-based methods. Ellis et al., 2023. Or leveraging language model-based techniques. Kai et al., 2023. In this study, the authors propose an agent workflow memory (AWM) that can induce, augment, and utilize workflows either offline from available examples or purely online during inference. The AWM was evaluated on WebArena and Mind2Web, showing significant improvements in task success rates, with relative increases of 24.6% and 51.1% respectively. Additionally, AWM demonstrated superior generalization abilities across different tasks, websites, and domains. The authors hope that AWM will provide valuable insights into dynamic memory building and significantly advance agent adaptations for a variety of digital tasks. Thank you for watching.